Erica Stanley. Just to tell you a little bit about me and why I'm speaking to you about Internet of Things today. First, I am co-founder and director of Women Who Code Atlanta. So we do a lot of things, from getting new developers started to helping women move further in their careers. We do a lot of workshops. And one of the things that I found is that there were a lot of women who were interested in getting started in hardware prototyping or hardware development, but a lot of the groups in Atlanta especially were very heavily male dominated. And so we needed to find some ways to kind of make people feel more comfortable getting started with Internet of Things and hardware. So that's something that I do. But also this is kind of, for me, this gets me back into some of my grad school research and using things like sensor development and some of the things that, I stayed in school for so long for. So this is, me getting to use my grad degree. So thank you. So I'm an 80s baby. I don't know how many 80s babies we have in here. So how many of us are waiting for the promises of the 80s? Where's my hoverboard? Because what they're calling a hoverboard, that doesn't hover, not a hoverboard. I'm waiting for my Jetsons lifestyle where everything is connected and everything is kind of working for me. And so, I think a lot of us born during that time and maybe even after are wondering where these things are, where are the promises of this awesome connected future? Well, the truth of the matter is it's not that far away. As soon as 2025, we might have self-regulated clothing that changes external temperature based on your preferences or based on the outside temperature. Medicines that are dispersed in real time based on your particular health needs. We might have office furniture that detects the stress in the body and the way that I need to be seated depending on, my posture, my height, my weight. Meeting notes that, are just on time, that just know what I need when I need it. So one way to get to this future that we feel we've been promised is the Internet of Things. And the Internet of Things is just a really buzzy word for saying connect all the things, right? So, you can have your appliances, your lights, even your pets. So my sister has this adorable Chihuahua that thinks that he's like a Great Dane. And so he goes around policing the whole neighborhood. And so when he gets lost, it will be really useful to know where he is so that the other dogs don't just devour him. So, that's something that you can use, a kind of connected device for. Our cars are going to be more connected. Cameras, all kinds of objects within your home. And really all of this is doing is just building on the hub that we've created already with our desktops and our laptops and our mobile devices. So using that as a hub, we're able to kind of expand this ecosystem of connected objects. So how do these devices actually work? So you have this constant cycle of sensing something in your environment and then communicating that somewhere and then doing some kind of decision making, some kind of computing based on that. And these are some qualities and some characteristics of typical connected devices. So they're hands-free typically, so you might be using some voice or gesture control, and that's something we'll talk about a little bit more into the talk, is that we have to think beyond your typical screen, touch screen type communication. It's always on, so that means that something you have to really think about is power consumption and connectivity. It's environment aware, so it knows where you are, it knows what's happening in your environment. Again, it's connected, it's attention getting, but that's something also that we have to be aware of, because let's say that you're in your car, maybe you don't want something getting your attention if you have to focus on the road. Also, you're going to be using a lot of third-party apps and a lot of ways to kind of connect this device to the outside world. So let's start to move into the technologies that are really building this foundation for the Internet of Things. And the biggest one is networking. So here is just kind of a diagram showing some of our networking options, and they're growing in scale with the height in this document. So, we can go anywhere from NFC, which is, just a few, inches to meter, to Bluetooth, which is a few meters, to Wi-Fi, which is more of an area. So think about that when you're building your device, because oftentimes it's a trade-off of how connected, how far you can be connected with power consumption with the data that you can actually transmit. So just looking at some of the contenders for networking in this space, and we see that Bluetooth and BLE in particular really wins in a lot of cases because of the low power consumption and what it's able to transmit. Well, BLE is great for state, so keep that in mind. And a lot of times when you have a connected device, you don't need to transmit video. You don't need to transmit a whole lot of data. So keep that in mind versus Bluetooth, which can transmit all of these things, but does not transmit state. So it's a bit of a trade-off, but when you're talking about devices that always have to be connected, that are really just transmitting state here and there or updates to state, you really want to think about BLE here. So the next thing are, microcontrollers, like smaller microcontrollers that can actually do quite a bit of computing. And so just looking at some of the open source microcontrollers that are out there today, we have the Arduino Uno, which is actually 2 processors in one. So you have your typical microcontroller from Arduino, and then which is much more like the Leonardo, if anybody remembers kind of playing with Leonardo kind of early in Arduino development. But it also has a Linux-based processor, so you're able, a Wi-Fi-enabled Linux-based processor, so you're able to do some things out of the box with the Uno that you can't with a lot of other microcontrollers. So that's something to keep in mind, depending on how important Wi-Fi connectivity is for your application. Also, you can actually enhance some of the scripts that you might be writing to communicate with sensors. You can kind of enhance that by creating scripts that run on a Linux machine. So using something like Python to actually do some of the computing from some of the data that you're getting back from the sensors. Then if you're interested more in wearables, which is kind of a subset of this Internet of Things space, then you might want to think about the LilyPad, because it's a fairly powerful device for being as small as it is. But one really cool thing, it has slots that allow you to sew it into fabric with conductive thread. So that's something that's really interesting about the LilyPad. Then you have the BeagleBone Black, which is always a contender. My personal favorite is the Photon. And one of the reasons, first of all, it's a Wi-Fi enabled microcontroller, so it has a lot out of the box. But another thing is Particle, oh, it doesn't look like I'll be able to. So Particle actually has their own cloud platform that allows you to kind of build for the cloud right from the beginning. So things like over-the-air updates, things like just being able to communicate with other REST APIs. And they've taken care of a lot of the things like security and scalability. You always want to be thinking about security, but it's nice to be built on top of a secure platform from the very beginning. And so kind of the extension of that is the particle electron. And the particle electron is really cool because it's based on cellular connections, so it's always connected versus, say, a Wi-Fi connection that's only connected when you actually make that connection. So that's something that's something that I'm actually working on. I don't have my particle electron yet, but that's something that's kind of on my list, my next toy. And then the tehsil is really cool because instead of just kind of figuring out how do these sensors go together, tehsil has figured this out for you. So if you look here, tehsil has all kinds of modules that are built specifically for the tehsil. And so you can, connect an accelerometer, you can connect a camera, you can connect, sensors for motion and LEDs. So it allows you to kind of build your device as you go, which is really important for prototyping because you want to have this figured out before you go into production. You want to know the combination of sensors that really help you build the device that you're working on. So next we move into sensors. So the sensors are really the nervous system of this ecosystem we've been talking about. So it allows you to kind of take in your outside world by understanding, moisture in the environment, by acting as our eyes, by incorporating things like computer vision to actually understand what's going on visually around us. All kinds of things that it can actually interpret because you're adding sensors to this ecosystem. So some common sensors that are used, and ones that we're really familiar with just from the sensors in our phones, for instance, are acceleration or proximity or orientation. But you can also have sensors for things like water leaks or sound or temperature and, of course, light. One of the best features of one of my tablets is that it adjusts to the ambient light in the room so that I don't have to kind of up the backlighting when I'm reading at night or take it down when I'm reading at night. So things like that. A few places where you can get some of these sensors, SparkFun is always a great place to kind of start if you're looking for sensors, even if you're looking for microcontrollers. Particle, there's several included with the Maker Kit. If you do start with a particle, that's my best advice, is to start with the Maker Kit, because you have a lot of things that you need to get started right there. And tehsil, as we showed before, they're sold separately as modules. So another part of this ecosystem that we're building is the ability to be able to host a lot of the data and to get that data back at any point. And also, at this point, we're hosting huge amounts of data. If you think about something as simple as your Fitbit, and how often it's updating the data that you're sending it with the sensors, with the odometer sensor that you have, that's a lot of data. And we're doing that on a larger scale with the Internet of Things. So that's something that's going to be a huge part of this, and figuring out not just how do we host and how do we process this data, but also what are the stories that we're going to be telling with this data. You don't want just numbers. Numbers don't mean anything to people. So we're going to have to find a way to make this data more human and to actually analyze it. And so that's something that's going to be huge with the Internet of Things. And then just a few kind of auxiliary technologies. We have, as I mentioned, computer vision, which helps machines see the way we do. It helps machines interpret visual data. We have augmented reality. So a lot of times people think of augmented reality as just placing images kind of in a projection manner in front of, say, a camera or some kind of visual display. But you can augment reality in a lot of different ways. For instance, Plantronics has been working on an augmented reality headset that augments your environment with audio, but also kind of tracks head movement and changes the feedback that you're getting based on your proximity to certain things and based on the rotation of your head. So there are a lot of different ways that we can kind of incorporate augmented reality into the devices that we might be building. And then there's machine learning and artificial intelligence. With all of this data and all of this that we're collecting from the user, it might be really useful to start doing some predictive analysis on that. And machine learning helps us to kind of take this from just responding to an event in the environment to predicting some kind of event in the environment for the user. So here are a few open cloud or open source cloud solutions for IoT. We have OpenStack. We have Apache Cloud Stack, which is Java-based. We have Particle Cloud Platform, which I mentioned earlier. And some of the really cool things about the Particle Cloud Platform are the over-the-air updates, the REST API that's available to you, and that is kind of already built in with a kind of a secure platform. It's very scalable, and it includes real-time messaging. A few other software development tools are Eclipse IoT, which provides open source implementations for many different IoT protocols. And also with Eclipse IoT, you can develop in either Node.js or C++. So that's really cool for some of the boards that are not, some of the older boards that may be very powerful, but maybe haven't kind of moved on or evolved to using some of the higher level languages. We have Hugin, which is kind of an open source, Rails-based, if this then that. We have Siteware and also Katiki. And I've used Hugin, and I'm actually working on a project based on that right now, and so far I'm really loving it. So I know that we're a bunch of developers and I know we're a bunch of technologists in the room, but when you think about Internet of Things, you have to take into consideration design, maybe a little bit more than we have in the past with your typical web or mobile app. Because when we're thinking web, mobile, we're thinking of screens, we're thinking of kind of touch interaction. But what happens when we don't have a screen? What happens when the interaction is not just touch-based interaction? So here is the Plantronics concept model I mentioned earlier. We have the fin, which is this the kind of white and blue ring object that you see there, and that's really just, it uses gestures of your fingers to kind of communicate different things in your environment. We have the Mio, which is a band that you put on your arm, and it detects the electrical impulses on your arm to navigate, different applications, different things in your environment as well. And this really weird contraption at the bottom is actually detecting brain impulses. And so at this point, thought is your interface. It's really cool stuff. And it's a little primitive right now, so you're not going to be able to do some really kind of complicated navigation of applications, but you can do really simple things like it'll train based on certain impulses that it's receiving from you, and it will, based on that training, you can kind of connect that to an action that you want to happen. So now that we're thinking about interaction beyond just screens, let's talk about the transition of interaction models. First, we started with command line, which is very static and very disconnected. We moved on to GUIs, which we've mastered now, right? And that goes along with a lot of the screen-based interaction that I was just talking about. But now, when we start talking about Internet of Things, we want to start moving into more natural user interfaces or organic user interfaces that are, kind of contextual and fluid, and a user just understands how to use this. And so when we start thinking about organic user interaction, we have this organic user interface model. And so a lot of the things you can do here are kind of described in this diagram. So when you're thinking of something that is not screen-based, what are the things that you can do? Well, you can speak to it. You can manipulate in different ways, so not just touch, but also, drawing. So one of my favorite, I'm an artist in my spare time, and I had not at this point found the device that made drawing as intuitive as it had been with, charcoals and pencils and that kind of thing. And so getting a stylus and just being able to kind of have a stylus that responds with pressure and all of this on a tablet just changed the experience for me, because that's how people understand that particular interaction. So that's what you really want to be thinking about when you're creating these connected devices. Think about how people just naturally interact with them. We also have gestures, so you have hand and eye gestures as well. So if we go into speech, speech is one that's used very heavily with the Internet of Things. And so you're going to start with, you're going to say something to your device. And that's going to initiate an audio stream that's captured by that device. It's going to go through this process of interpreting the meaning based on the dictionary that you have. And depending on how complex you want the conversation between you and the device to be, you need to have either a really robust dictionary or you can have a really simple dictionary. But one of the things that it's going to do to determine what you're saying and to kind of process what you're saying is that it's going to call on experiences that you have shared with that device. So it's going to kind of learn gradually and become a better conversationalist based on your experiences. And the vision for your system will determine how you put these components together and what components that you use. Again, for instance, how robust is your dictionary for determining the processing for your natural language? And when are we going to be using voice interfaces? This is probably going to be cases where touch interaction is not desired. So you're going to be doing kind of in-car interaction, something where your eyes and hands are occupied, medical environments where you don't want to kind of spread a lot of germs, security, because it can be a very powerful mechanism for identifying a user, and other kind of shared experiences. So now we move into the manipulation portion of the organic user interface model. And again, these are natural, real-world interactive interactions. So there's two main types. There's deformable and non-deformable. Non-deformable is when the object is not changing shape because of your interaction with it. So that's your basic screen-based touch, texting, tangible handling of that object. But when we move into deformable user interfaces, you're thinking more of something that changes its shape because you interacted with it. And you want to keep, for instance, like clay. So there are some studies where people are using kind of clay that has certain sensors in it so that it can respond to kind of the user interaction, and you're seeing what you're building on screen based on that interaction with the clay that has these sensors. So that would be an example of a deformable user interface. So the input for these interactions are using kind of freehand manipulations that change the shape, and they rely on skills the users already have. If you have some kind of interface that requires a user to shape something, a user automatically knows how to use their hands to shape something. So this is something that would be really good to use in that case. So this is great to use, again, when the physical form complements or enhances the function, kind of like the example I just gave. Where precision or accuracy is desired, we're very good at making small movements with our hands and being very accurate there. Public places where voice or gesture tracking would be difficult or perhaps frowned upon. You would want to avoid this when your hands are likely occupied, when you're driving or cycling, and also medical situations where, again, you may want to keep all of the things you contact sterile. So some best practices: in 2D spaces, you want to ensure that you have about 15 millimeter surfaces radius for interactive elements. And this isn't all that different from a lot of the things when you're building interaction patterns for mobile. For instance, you always want to make sure you have that about 40 pixel square area for finger interaction on mobile devices. So it's very similar to that. In 3D spaces, you want to consider a visual feedback for movable objects so that the user actually knows what's happening. And you also want to make sure that you have something like that so the user doesn't think it's broken. So you want to make sure that it's kind of real-time feedback there. You may want to consider haptic feedback if you're working with touch-based or deformable models. And you want to, again, respond to every contact with immediate feedback. And you want to enable basic direct manipulation. You don't want to have, for instance, the equivalent for a touchscreen would be nested, pretty much nested menu hell. Like, you don't want to do that for these kind of interactions. You don't want to have really complex interactions that are coupled together to do one action. So that's not really what you want here. And so now you're moving on to gestures. And so you can have in-air gestures, like all of the hand movements I'm doing right now. Speech, like speech, is one of the oldest forms of communication. And this is used to either issue a command or communicate with devices. So if you've used Xbox or anything that uses your gestures to make some decision or perform some action, that's what this is talking about. And you must design the system to capture gestures, capture hand movements, so you have to understand how hands typically move, right? Facial expressions, body motion, eye tracking. You would use this when the interaction is with a large display or situations requiring you not to touch anything. You would want to avoid it where errors can have life-threatening impact, because again, you have to train the system to understand, for instance, how hands move and how eyes may be moving, and it may interpret that incorrectly. So you don't want to, base something that's life-threatening on that. You want to avoid time-based gestures as they kind of, delay power users who are going to be making a lot of gestures. You want to clearly communicate the start and stop for a gesture. So if this is your gesture, you want to make sure that you don't have, say, a gesture that has just one kind of enhancement to that, because that's going to be a little bit confusing to your system. So you want to have very clear start and stops. And you want to handle false gestures you know, kind of false positives and false negatives. Another recommended micro pattern or interaction pattern are micro interactions. So these are contained product moments that revolve around a single use case. Again, like I said earlier, you don't want to have a lot of complex gestures or a lot of complex interaction. You want something that's very simple and brings about a very simple and expected action. And so now that we've kind of combined the technology that is the foundation of Internet of Things, and we talked a little bit about how you would consider designing for these kind of connected devices, now we can kind of move into prototyping, because this is really a mix of design and technology in the thinking and the making of it. And it's fundamental to creating projects with new features, something that you really want to kind of enhance something you already have. It's really important to think about the tech as well as the design. This applies even more to Internet of Things, since hardware is usually involved. And so when you're building your team, this is really interesting, because in a lot of cases you have either a hardware team, either a design team, or a software development team. But this prototyping, this kind of prototyping really requires everybody to be working together. It requires, instant feedback from software developers, from, designers, from your hardware developers. So you want to build a team that has overlapping skills. So you want somebody who, for instance, understands the hardware side and the software side. You want someone who maybe understands design, but also understands hardware. So, you're going to want to have, someone, again, who understands UX, a software or embedded engineer, and maybe an electrical engineer or your hardware person. Hackathons are a great way to kind of find that team, because where else do you find all these people just kind of randomly in the same space? So hackathons are a great place for that. And you want to look for hackathons that are focusing on either Internet of Things or wearables. And so really what you're doing, you want to kind of build this on a lean collaborative process. So you want to learn, from your prototype, and then build and measure. And you want to do that in this cycle of just kind of collaborating with these people at the table. And so how do we combine, kind of the design thinking, when we're talking about interaction models and kind of building products based on this, which is kind of design thinking and kind of lean. How do we combine those? And from that, we get design sprints. And so this is this constant cycle of understanding your problem, understanding your audience, defining what you want to build based on, or defining clearly your audience. And then the diverge point is when you're kind of figuring out, what can we do? What are all the things that we can do in this space that will meet the needs of this audience, that will solve the business problem? And then you kind of converge, you decide on several of these features, and you start building a prototype based on that, and then you start validating it. And you just go through this process continually until you feel like you have the right product. So the first step is to understand. And so this is where we want to figure out, who are our users? What's the context? What are their needs? So you really want to understand that very well before you go any further down this process. Then you want to do that step I mentioned, diverge. This is where you come up with all of this is the brainstorming step. You come up with all of your ideas, anything that you could possibly think of that will meet these users' needs. And it can be almost fantastical. It can be whatever you want at this point. We're not worried about feasibility here. And so a part of this is when you find that critical user story for the user that you've just defined. And this is going to highlight, the story most critical to the challenge that user has. And you're going to make sure that you kind of diagram where your customer starts in this process and where they should end up, and what needs to happen along the way. And what this allows is kind of inspection of the inventive aspect much sooner in the prototyping process. You don't want to get all the way to the end of that step I showed you before, this validate step, to realize that, oh, maybe we should have done something a different way. You want to be thinking of your user from the very beginning of this process. And so that's what that helps you to do. Then, based on the critical diagrams that you and the team have come up with, you're going to decide on what is the most important user story, and you're going to storyboard that idea. Once you kind of have a storyboard, then you're ready to prototype because you've thought this through now. You've thought through the interaction. And you can build something kind of quick and dirty to show your users. It can be a paper prototype, or it can be a little bit more high fidelity. And then you're going to validate that. You're going to kind of test that with people. You're going to be doing a lot of user testing and kind of user discovery here. Well, you've already done your user discovery, but you're going to go around to your potential users, kind of ask them, how would they use a system like this? How could we make it better? And then you're going to kind of go right back to the drawing board and figure out how you can make this continually better. So that was the typical process of design sprints for, say, maybe a software product. But now how do we take that and move that to this really integrated team of hardware engineers and software engineers and designers? So in the first step, we're going to perform that together. We're going to understand our customer, our users. We're going to understand, what drives them and what are their problems and what is the challenge. And we're going to clearly define that. But at that point, during the diverge cycle, we can have our hardware engineers going off to figure out what in the hardware space makes a lot of sense to solve this problem. We can have our software engineers kind of going off and figuring out what is it software-wise? Is there a mobile app that can solve this problem? What can we do with software? And we can also have our designers thinking about that. So the diverge process you can actually do separately. But then you're going to come back together for the decide. And this is where we're bringing all the ideas together and we're figuring out that critical path diagram. And so once we've come together, we've decided that this is, a great idea, or we have some really great ideas, and this is the idea we're going to work on, then we break up again. And we have, on the engineering side, we have the breadboarding and the conceptual hardware testing. On the designer side, or on the UX side, we might have wireframes, might be developing wireframes. And something that's really cool when you're in this design phase for the hardware, a really cool tool to use is Fritzing. So Fritzing is an open source electronic design automation software. And it aids in collaboration because it's actually really simple to use. And you can import a lot of those boards that I mentioned earlier. You can kind of import them and move things around and see what this does to change the prototype that you're building, the hardware side of it. And designers can kind of get involved as well here. So this is something where everybody can get involved if necessary, and it's just very easy to use. So now that we have the step where we have our hardware engineers kind of working on their design, and we have the designers working on the wireframes, then we also want our software people thinking about the data modeling. What is the data that's going to be processed with this solution that we've come up with? And we want to be thinking about that because we want to think about, again, we don't just want to throw data up to the cloud. We want to create stories that are actually going to help people use this product to make this a really usable product. And so that's what our software engineers can be doing at that point. Software engineers, data scientists, that kind of thing. Then we'll come back together and we'll start working on the low fidelity prototype. And so this might be something that's, maybe you started with a particle, or maybe you started with an Arduino, and kind of putting all these things together. Some of the things from the wireframe, some of the things from the data modeling. We're going to start working on the firmware at this point. And from that step, we're going to have kind of an alpha prototype, kind of the hardware and the initial firmware. From this step for the UX side, we're going to have visual design and kind of the specs from a visual standpoint. And now we're working on the UI development. And keep in mind, this doesn't have to be your typical screen-based UI development. It could be, some of those other interaction models I described earlier. And so now pretty much we've built the system at the step before. Now how does the user interact with it? And we're taking into consideration, things that we came up with in the step where we developed the wireframes, and also the step where we were doing the visual design specification. And at this point, you can put that together and validate. And in the validating, we might also determine that we want to build a higher fidelity prototype to really test some of these things out. And so when we get to high fidelity prototypes for connected devices, 3D printing is really helpful with that. So you want to use a really decent 3D printer. You want it something with greater than 100 micron resolution, preferably, or less than 100 micron resolution, preferably 50. You want it to be able to print numerous material types, including flexible materials. and you're going to have this test loop where you identify candidates for field testing. You don't want to get to this high fidelity stage without really vetting some of the low fidelity prototypes that you were working on. And because, they're not terribly expensive and the material that you're using is not terribly expensive, you want to iterate really quickly and make any necessary physical changes here, certainly before you decide to move this into production. This is where the mistakes are made. This is where you can kind of fail fast. And just thinking of some applications of a connected device design sprint, we have, your basic hardware MVP. I mentioned hackathons and hardware projects involving teams, and adding features to an existing connected device. And so that is pretty much it. Let me see if you have any time for questions. We have like 5 minutes, so I can take some questions if you have any. No questions? I think we'll wrap it up. Thank you.